Hi class. Now I'd like to talk about a very important class of integrals for which contour integration can be used. And in order to do that, we need to cover a topic called Jordan's lemma. We want to think about integrals of the form, the integral from minus infinity to plus infinity of e to the I kx f of x dx, where k is a positive constant. We see integrals like this all the time when we talk about Fourier transforms, which is one of the topics we'll discuss later in the class. Analytically continuing, e to the I kx f of x becomes e to the I kz f of z in the entire complex plane. But for k greater than 0, if you think about what happens in the upper half plane, e to the I kz goes to 0 exponentially fast, because in the upper half plane, the imaginary part of z is positive, and for k positive, e to the I kz then goes to 0 exponentially fast. Of course, it's easy to see what we would have to do if k is less than 0. In that case, we'd have to think about the lower half plane. Given that the integral goes to 0, or the integrand rather, goes to 0 exponentially fast in the upper half plane, we could consider taking the contour which we start with, which is the integral from minus infinity to plus infinity, and closing with a very large circle in the upper half plane, or rather semicircle of radius r. If we think about this contour, then in the limit as r goes to infinity, we get two pieces. The piece we want, the integral from minus infinity to plus infinity of e to the I kx dx along the real line, plus the integral along the upper circle. And this is where Jordan's lemma comes in. Jordan's lemma says if f of z goes to 0 uniformly independent of theta as the radius goes to infinity, then the integral goes to 0 in the upper half plane. The integrand along the upper semicircle goes to 0. So this assures us that even if f of x only goes to 0, for example, linearly, as we'll see in the next example, then this extra piece goes to 0 because of the additional convergence provided by the integral, by the exponential piece of the integral. So considering the contour we've closed in the upper half plane, then we see the integral from minus infinity to plus infinity of e to the I kz f of z becomes just 2 pi I times the sum of the residues in the upper half plane. And so long as Jordan's lemma applies, then the extra piece we'd get by closing in the large semicircle vanishes. I will post the notes of this lecture online in case the upper part of this slide is cut off. Let's take a special case. Say we consider this integral it, this represents the current as a function of time, is some constant divided by 2 pi times the integral from minus infinity to plus infinity e to the I omega t over r plus I omega l d omega. This is the current which we get from an RL circuit, where R corresponds to the resistance and L to the inductance. Here, omega is the frequency, and of course frequency, if we do Fourier, this is actually the result of solving a problem using Fourier transforms. The omega is the angular frequency, and it's real. But again, we can consider analytically continuing this to the complex omega plane. We want to do the integral from minus infinity to plus infinity, and we'd like to see what we can use, if we can use Jordan's lemma to figure out what the value of this integral is. Now, if we go to the complex omega plane, then we can look for a pole of the integrand where r plus I omega l vanishes, which is to say at omega equals I r over l, which is to say that the pole of the integrand occurs in the upper half plane. Now, in this case, t represents time, and we actually have two possibilities, t less than 0 or t greater than 0. If t is less than 0, then the constant, as far as the integral is concerned, t is a constant, and in order to do the integral, we should close in the lower half plane, because with negative t, we need the imaginary part of omega to be negative in order to get a convergent exponential. But you'll notice in the lower half plane, there are in fact no poles. So that immediately tells us that I of t equals 0. There are no poles when we enclose the lower half plane, and therefore the integral from minus infinity to plus infinity for t less than 0 actually vanishes. We'll talk about that more in just a second. For t greater than 0, we close in the upper half plane, and in this case, for t greater than 0, we do pick up a contribution from the residue at I r over l, and the current, I, as a function of time, exponentially decreases in time. So This integral actually has a very interesting behavior. I of t is 0 for t less than 0, and it's exponentially falling for t greater than 0. In fact, this representation of the current corresponds to a pulse of voltage applied at time t equals 0. And for t less than 0, there's no current because causally there can't be current flowing before you've applied a voltage. Whereas for t greater than 0, there can be a current, and in fact the current is exponentially decaying. And so this is one of the features that we'll see often in integrals of this type. Depending on the value of the parameter, for t, in this case t, for t less than 0, t greater than 0, we can have very different dependence. And that's going to be reflected in our study of Fourier transforms and corresponds to a physically sensible result. In fact, corresponds to causality. Let's consider one more example of using Jordan's lemma. Let's consider the integral from 0 to infinity of cosine mx over 1 plus x squared dx, where m is a positive constant. Of course, this is just a convention because, in fact, cosine minus mx and cosine mx are the same thing. So by convention, we can take m to be greater than 0. Instead of computing this integral directly, let's consider an alternative integral, which is of the form where we can apply Jordan's lemma directly. Let's consider the integral from minus infinity to plus infinity of e to the I mx over 1 plus x squared dx. E to the I mx is cosine mx plus I sine mx, and that denominator is 1 over 1 plus x squared dx. Notice that the denominator is even, the cosine mx term is even, but the sine mx term is odd. Therefore, when you integrate from minus infinity to plus infinity, the sine term drops out, and in fact, these terms being even, the integral from minus infinity to plus infinity is just twice the integral we want, the integral from 0 to infinity of cosine mx dx over 1 plus x squared. So if we go back to this integral, the auxiliary integral, the integral from minus infinity to plus infinity of e to the I mx dx over 1 plus x squared, well, e to the I mx over 1 plus x squared analytically continues to e to the I mz over 1 plus z squared. This is an integral which vanishes exponentially in the upper half plane, so we can use Jordan's lemma. The function 1 over 1 plus z squared goes to 0 faster than 1 over r squared at large distances r. It has poles where the denominator, 1 plus z squared, has zeros. It has poles, simple poles at z equals plus or minus I. So when we close this contour in the upper half plane using Jordan's lemma to evaluate the integral, we get 2 pi I times the residue of the integrand at z equals plus I. Since this is a simple pole and it's a ratio of two functions, we just get the numerator evaluated at the pole divided by the derivative of the denominator, 2z, which at I is 2I, evaluated at the pole. So these cancel out, and we get pi e to the minus m for our overall integral. But remember, this auxiliary integral is twice the integral we're actually interested in. Therefore, the integral we're interested in, the integral from 0 to infinity cosine mx over 1 plus x squared dx, is pi over 2 e to the minus m. A couple of easy ways to check this. First, again, this is a real quantity, which is good, because it wasn't obvious, especially given all the i's over here, that things would turn out to be real. Furthermore, when m goes to 0, this is just the integral from 0 to infinity dx over 1 plus x squared, an integral we've seen a number of times, which we know is equal to pi over 2.